Hello, welcome back. We are going to spend today talking about the 10 parent functions that we will be studying throughout the entire school year for Algebra 2. So we will be looking at each one of these in their simplistic form today. And then each of the following units are going to correspond to one or more of these parent functions, depending on how they relate to one another or how they fit together in the curriculum. Important thing to understand is that these are the 10 that you will be studying for the remainder of the school year, and you're going to need to become experts on everything that they have to offer. So we'll be learning about the basic fundamentals of each one today. The first thing you're going to want to fill in for today's notes are going to be the definitions of these three terms. Your first term is your parent function. Now, it is the simplest function with the defining characteristics of that particular family of functions. So in this particular case, we have the linear parent function first. And everything from the linear parent function is a transformation, which we're going to study tomorrow. Vertical symmetry shows that the function has a vertical line of symmetry, typically at x equals 0. Rotational symmetry means that the function is symmetric when it's rotated 180 degrees around the origin. So you're going to want to fill out each one of these different categories. If I move more quickly, then you're able to copy down this information, and please just pause the video so you don't get behind. So notice the equation for the linear function is y equals x. That should be familiar to you. Y equals mx plus b is a form of the linear parent function, a transformed form of the parent function. The domain and range are pretty clear. Notice there's no restriction. This line moves in two directions, left and downward, and this segment of the line moves in two directions also, up and to the right, and there's no restriction on either one of those movements. Notice that we've added in two categories here that describe where or the direction that the graph is traveling. Okay? So if you'll notice that the graph is always increasing throughout the entire interval of its existence, and it, of course, is never decreasing. In order for the parent function to have a decreasing situation, we have to transform it. Therefore, it is no longer a parent function. This is end behavior. End behavior points out what is the behavior of the graph as the x values get extremely large and likewise extremely small. And behavior is very important when we start talking about rational functions later on in the year. But notice as x gets large, y also gets large, and likewise as x gets small, y gets small as well. That would be known as a direct relationship. Notice here that there's no concavity and only rotational symmetry. We're going to get back into concavity in just a few minutes when we have a couple of examples under our belt. These are some critical values. The critical values are going to play a very critical role in the way that we describe and the way that we graph accurately transformed functions. So please use these to help you as a baseline model for actually drawing your own graph on the graph that has been provided to you. So begin by putting an ordered pair at -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. Then take a straight edge and draw a line accurately through each one of those 5 points. That's going to give you the baseline for how you're going to use transformations of parent functions later on in this unit and through the remainder of the school year as we study each one of these different functions. Our second function is known as the absolute value parent function, and we get back to those vertical lines. Y equals the absolute value of x is the way that this is stated. Notice from the graph that our domain goes from -infinity to +infinity. However, the range does not have that same interval. notice that because of the nature of the absolute value symbol, our range is now restricted from 0 to infinity. So when we study the absolute value, we'll understand more why it is that it does this. The absolute value is defined as the distance from a particular location without regard to direction. And as we know, distance cannot be negative. So increasing, it's going to be increasing over a certain interval, and likewise decreasing over a certain interval. So we're going to take a look at the direction. The thing I like to do is I like to place an imaginary ball on the graph. If I go all the way to negative infinity, follow this line out to wherever it ends, and I place an imaginary ball on that, do I have to roll the ball up by pushing it, or will it roll down by itself? Well, it'll clearly roll down this line by itself. And that is how we understand whether it's increasing or decreasing. And we can go further as to say, well, where would it be that the ball would actually stop rolling when we were rolling it down this particular part of the line? And that point is 0, which is why it's decreasing over the interval negative infinity to 0. Likewise, if I take that ball and I try to put it on this part of the line, notice I would have to actually manually push it up the line, or else it would just roll back down. That means that it is going to be increasing from that point onward. So hopefully that helps you visualize how we find increasing and decreasing intervals. Again, the critical values are going to be the way that you specifically graph these, so please use that as a guidepost. It's going to be very important for you to do this because it's going to help you when you come to your transformations of functions accurately. Notice that concavity here, again, is none. All right, so we're starting to see a pattern here in the words concavity, even though we have two different parents. All right, moving on here, we have a vertical line of symmetry at x equals 0. The end behavior, notice, as x gets very large, y gets large, and as x gets very small, y continues to get large. So based on the picture of the graph, you can surmise what your end behavior is going to be by simply stating what the graph is doing when x gets extremely large and extremely small. All right, moving down here, our next parent function is our quadratic parent function, y equals x squared. The domain and range are negative infinity to positive infinity and 0 to infinity. The nature of this graph shows a curved line. This is our first parent function that has a curved surface as opposed to a straight line. All right, so now we're going to go ahead and look at its increasing and decreasing intervals, and notice those are the same as our absolute value parent function from above. If you want to use that ball example, you can see clearly how that actually works. Again, the end behavior similar to our absolute value, not similar, exactly the same as our absolute value above. But now we have a new type of concavity, and this concavity opens up. And this is where you're able to see what the difference is in determining whether or not a graph has or does not have concavity. So we notice that this line does not have a constant slope, and it's clear to see that when we go ahead and look at the critical values of the graph. For our constant changes in x, we do not have that same constant change of y. All right? So that means we do not have a slope of a quadratic function. So what that means is that we have this curved surface which now has concavity. So linear surfaces do not have concavity, but curved surfaces do. And then opens in an upward direction. If you want to think of it as the mouth of a cave, this is going to be the cave inside of here, and it's facing upward, so that's opening up concavity upward. Again, we have a vertical line of symmetry, and now you can see your critical values as well. Moving on to our next set, we have the square root parent function. The square parent function is y equals the square root of x. Domain is restricted from the interval of 0 to infinity. Likewise, so is the range. Thinking back to what we did yesterday in discussing our restricted domains, you remember that square root functions, when they have a negative radicand, they have imaginary solutions. And you'll notice here that there is no negative portions of this particular parent function in any way. Our end behavior, or our increasing interval, is from 0 to infinity, and notice we would have to push this ball up, 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 all the way through, and there would be no place for it to drop, so there is no decreasing interval for this particular function. As we get very large, y is going to get very large, but notice, as x gets extremely small, y does not exist. That's a very important distinction here. Our end behavior, well, there is none for the negative values of x. The end of this graph is actually at 0. Concavity, that is incorrect. Concavity is not none. I'm sorry I did not catch that before. I'm going to make that correction right now. We're going to scribble that out. Our concavity is down. This one's a little bit trickier to see, but you can see how the curved surface is right there. So this is the inside of my cave, and the inside of my cave is facing downward, concave down. All right, moving on to my cubic parent function. So cubic parent function is y equals x to the third power. Domain and range are not restricted in any way, so our intervals are negative infinity to positive infinity. Notice if I put a ball down here, I will always have to push it up, 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 up. There is no interval over which this is not increasing. That's very important to understand because it looks like it might start to decrease here, but it does not. It always continues upward, up, 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 always increasing. So as x gets very large, y gets very large as well, and likewise very small gets small. Notice we have concave up and concave down. Let's take a look at this. Notice that you have a curved surface here, which is facing roughly downward. Notice you have a separate surface here, which is facing upward, and that's how you get your concave up and concave down concavity for a single parent function. Rotational symmetry is at play here. I can rotate this thing 180 degrees, and the arm of this will rotate to there, and the arm of this will rotate to there. And that's how you get your rotational symmetry of 180 degrees. Cube root parent function, notice here, is y equals the cubic root of x, just like the square root, except our index is 3 instead of 2. Domain and range, much like the inverse up here above, is going to be the interval of negative infinity to positive infinity. Again, it is always increasing. There is never a decreasing interval for this particular parent function. Just like before, as x gets large, y gets large as well. As x gets small, so does y. This is important to understand because what this looks like could occur is this eventually would level off and flatten off. It never does. This always curves upward, regardless of how far you go in the positive or negative direction. It never goes horizontal. Concavity again, concave up and concave down. Let's find those curved surfaces so we can see clearly where this concavity is coming from. So you see that you've got those two separate curved surfaces which create that concavity there. Again, the rotational symmetry, much like I showed above, is 180 degrees. Our last set of parent functions are going to be our reciprocal or rational parent function. It's called both, so please be familiar with both of the vocabulary terms. A rational, a ratio is a fraction, so that's where the word rational comes from. All right, so we get y equals 1 over x. The domain of this, if you think back to what we talked about yesterday with our restricted functions, is everywhere except for where the denominator is equal to 0. Since the denominator is x, that means that x cannot equal 0, and that becomes our undefined term. Okay? So notice what happens here. we are going to be looking at our end behavior when it's increasing or when it's decreasing. So I'm going to go ahead and put my imaginary ball here, way out at the end. And notice what it does. It rolls down and then falls off. But then I'm going to go ahead and take that guy, I'm going to put it up here. And notice what happens. It rolls down and down, down, down. Therefore, we have a decreasing interval throughout the entire graph. Notice our end behavior all of a sudden. It has changed from all of our other parent functions. So as x gets really big, that's out here, okay? Notice what y is approaching. Y is approaching something very special. That is called an asymptote. We're going to talk more about asymptotes later. But know that an asymptote for this particular exercise is an imaginary line that the graph approaches and never crosses or never touches. And we're going to call that also a limit. Notice likewise that this branch of the rational parent function does the exact same thing. As x gets very, very small, that's way out here, notice it approaches that imaginary line again of 0. That's going to be very helpful for us because we can map the asymptotes and then we can draw the transformations from those maps. Notice we have concavity of both up and down. Let's take this curved surface first, and there's your downward facing cave, and here's this curved surface, there's your upward facing cave. And it also has rotational symmetry. If I take this branch, rotate it 180 degrees, it will map onto this branch, and likewise that one up to there. That's why it contains both. Notice we have some fractions, and we also have some undefined values as well in our critical values. All right, the constant parent function, for some the easiest to see, but others this c value is a little bit confusing. The constant parent function is y equals c. If you remember back to your days of HOYVUX, this should make a little bit of sense. So we're dealing with a horizontal line where y equals a number, and you can pick any number you want. Notice for my graph I chose 4, but you can pick anything you want for yours. It's no big deal to me. The domain is always going to be the interval of negative infinity to positive infinity, and the range is going to be one number. It's whatever number you pick. So in this case, my range is 4. Notice it's never increasing and never decreasing. That's what the O is for in HOY. That's a 0 slope. And notice that as x approaches infinity, y is c. Doesn't approach it. It is the value of c. Okay? There is no concavity. Think back. Concavity means curved surfaces. Concavity curves. And now we're back to straight lines. That's why it has that. Notice this one has vertical symmetry as well as rotational symmetry. And then because I picked 4 for my number, I would fill in 4 as my table values, but I just chose C to keep it generic. Exponential parent function. We're going to study this more towards the end of the school year. This is a very good one when it comes to any sorts of compound interest or growth or decay. Notice we have an equation here, y equals 2 to the x power, where x is the exponent. And you're going to see base numbers for your parent as either 2, 3, or 10. They can be any of those. Notice they're all parent functions. Okay? The domain is going to be negative infinity to positive infinity, and we're going to introduce that term of asymptote again. This graph has a limit. That limit is 0. That's the asymptote that it will approach and never touch. Okay? We have an increasing interval from negative infinity to positive infinity, and it's never decreasing. So we have, as it approaches, as x gets very large, so does y. But as x gets very small, y approaches that asymptote of 0. Concave up, symmetry, there is none. And here are your critical values. Our last and final parent function is the logarithmic parent function. That one's going to be a y equals log base 2 of x, where the base of the logarithm is any number, but we're going to really focus on the numbers 2, 3, and 10 for our parent functions. Domain, 0 to infinity. Range, negative infinity to positive infinity. Notice it's always increasing and never decreasing. Just like the square root parent function, you'll notice you have an end behavior where as x gets very small, y doesn't exist. That's because now we have a vertical asymptote here, which the graph can never cross. Anything beyond that is undefined. Okay, concavity down, no symmetry, and here are some values for this particular parent function. Now, I hope that you were paying attention as we were going along and you were starring these parent functions because they are inverse operations of each other. We're going to study each one of them in depth at different times during the year. So please go back, if you have not done so already, and take a look at your inverses so that you have a clear understanding of what those are.